So is it okay?
Yes, sir.
Okay. And in magnetic transducers, what we have done, we have discussed actually MR based sensors, these magnetoresistance, and we generally discussed mainly GMR, magnetoresistance, where a large change of resistance is observed when we measure it under the influence of magnetic field. And magnetic recording heads, one example was discussed. And another sensor which is involving actually magnetic effects or magnetism is a Hall sensor. And in general, there's a conversion of magnetic field into electric field or an electric current or a voltage, and you measure that. So in Hall sensors, the basic principle that on which they work is Hall effect. So they work on actually Hall effect. Hall effect you all know actually. You have a sample. Sample means any material. It may be a metal, it may be a semiconductor. So there is a Hall effect in metals as well. We are mainly dealing with it with semiconductors. So let's consider that if it is a semiconductor, we will assume that a Hall effect is observed in semiconductor, but there is a Hall effect in metals as well. I have sent you the notes and those material. If you see there,
मेटल क्या इंफॉर्मेशन देता है हॉल इफेक्ट?
हाँ क्या हुआ
सर ये कौन सी इंफॉर्मेशन देता है हॉल इफेक्ट इन
मेटल्स? देखो
मेटल्स?
हॉल इफेक्ट की इंफॉर्मेशन क्या है, ये आपको हॉल इफेक्ट आप वोल्टेज मेजर करते हो. व्हाट यू फाइनली मेजर? यू मेजर हॉल वोल्टेज. Okay, and yeah, you measure VH actually. So in Hall effect you measure VH, sorry, so you measure VH, which is equal to actually IB divided by this charge. This is actually N C, you have it is N, that current density, charge density, into thickness if it is H of the Hall sample. And I have drawn here as diagram in the above. Let me see it where it is. Yeah, here it is. So if you see it, this diagram is here. So this is simple configuration. What you measure Hall voltage along these directions. There's a separation of charge carriers, my negative, positive, negative, positive. And we make use of this Hall voltage for particular application, or Hall effect for particular application. We will discuss one of many applications or one or two applications in this during this session, and you will be able to understand then how it is used actually. It can measure it is a Hall current sensor. There is a sensor which uses Hall effect but measures the currents. It can be also measured to check the position of different objects, and we will see how that is done. These are the simple examples. Before that, we rewind this Hall effect, that is actually VH Hall voltage, which is developed across this semiconductor or a material. And if you see in this case, this VH, yes. So if you see this VH, it is equal to, and from the above expression, you can see that it is directly proportional to I, that I is mainly in the X direction. It is directly proportional B, let us suppose it is in Z direction, and this VH is inversely proportional to 1 by T, thickness of the sample. So why I am writing is this, is that if you see that from this expression, Hall effect expression, this VH is not dependent on the thickness and the length of the sample, but it is dependent on the current which is here. And this current, if you see, this current has a dependence. This I is equal to actually current density into thickness into this width. This is a width actually. This is not a thickness, is the TH, width of the sample, and this TH. So it means that you increase this TH, the current will increase. Okay. This TH, that means I is directly proportional to TH, but also your VH, this VH is inversely proportional to 1 by TH. So what it means is that you have to make a proper choice of the thickness of the sample to get the maximum of the Hall voltage. Because when you increase this TH, your Hall voltage will decrease, but this Hall voltage is directly proportional to the current here. So there's a trade-off actually. So you have to maintain a balance between these two. That means thickness and the current. So thickness means, so you have to choose a proper thickness. If you increase it too much, your Hall voltage will drop. If you decrease it too much, your current will drop. So because I is directly proportional to TH. So we have to make a balance between these two actually. And therefore, these in Hall sensor designers, there's a trade-off between choosing a small thickness TH while maintaining enough current I to flow through the sensor actually. So we have to maintain this thing. And we have seen that how it depends. Now, coming to the next point is that we have taken a sample or material which is in the rectangular shape in the above. But you can have many shapes. Generally, theoretically, physics should be remain same. The shape should not have an effect on the theoretically on the Hall voltage, but it has been seen that in reality, geometry of a Hall sensor or a Hall sensor does affect VH output. That means Hall voltage is what you measure in the output actually. Then you can convert voltage into current. You can convert that voltage into some another signal in a frequency using different circuits. So VH actually it also depends upon the different those geometries of the Hall measurements. And if it depends upon the geometry of a device, of a sensor, Hall sensor, that means what is the design of that particular Hall sensor you are, is it a circular, it is a rectangular, it is a cylindrical, whatever the configuration or the geometry of that Hall sensor is, then we introduce a geometry factor. Geometry factor, GH. That geometry factor be equal to GH. And when you have different geometries, you can calculate VH is equal to GH. This is Hall, what is this? This is Hall coefficient actually. It's not Hall voltage, not resistance. I into B. Simply, it is derived from the dimensions of the material. And for rectangular Hall element, if you see, you know that you calculate R is equal to rho into L by A. So this is where the change in geometry leads. The current will change. That is to this L and A will change. So it is rho L divided by W into EH. And you know the symbols, this is the width of, this is thickness, this is the length of the material of this sample. And similarly for different configurations, you have different dimensions. So if you have a metal, you are using a metal sample for Hall sensor. So the rho resistivity of the metals is characteristics of those metals itself. So that there are no external factors actually which will affect the resistivity of the metal. So that means if you have a metal, it has a resistivity rho, so it will be affected by internal factors because you are not doing externally something except giving some potential to measure the current. But if a semiconductor, this resistivity, that is current or the Hall effect, it can be changed or measured under different doping concentrations. Doping concentrations, it can be varied having different mobilities of the charge carriers. Mobilities of the charge carriers. So we can vary. We can make two materials. We can take two materials like P material, N material of a semiconductor, and then design a Hall sensor. So that is also a possibility. Simple how the Hall sensor is operating actually. What is the operation principle of Hall sensor? operation principle of Hall sensor or operating principle of Hall sensors. They simply the simple principle is that they work on this Hall effect, which we have discussed above, and we take a material which is a semiconductor or a metal, and current which is passing through it in the presence of a magnetic field. The voltage which is generated perpendicular to B and I, that is VH, and this VH is measured, but the problem is that the VH which is measured in a semiconductor is small. It is very small. The magnitude is very small. When the magnitude is very small, what can be done? We can use amplification process, and the amplifier circuits are used. Amplifier circuits can be used for amplifying this small signal. When we amplify this small signal and we take its output, measure then that amplified signal actually. The advantage of these Hall sensors over other sensors is that since sample thickness is very small, thickness is low, okay, the thickness is very small. When the thickness is very small, it can be integrated. Hall sensors can be integrated. Hall sensors can be integrated along with onto a single chip with amplifier circuit. With amplifier circuit and signal processing devices, which is called signal conditioning actually. If there's any noise, you can remove that noise. Like there's a lock-in technique actually. There's one technique which is called lock-in technique to remove the noise from the signal. And that can be both integrated onto a single chip, mostly silicon, on the silicon. So we use the Hall sensors of the silicon material, silicon semiconductor. And this allows actually, what does this do? This allows, from using this process, we can have very low cost and high volume production. What is happening? High volume production. That means we can create a large number of Hall sensors at very low costs. These can be also, these are actually surface sensors. They can be mounted on surfaces. That means we can mount any Hall sensor. You take a Hall sensor, small strip, and you can mount it on the surface on that. And that means if you have a PCB, printed circuit board, PCB, you can take a simple PCB, printed circuit board, and place a Hall sensor here along with the different components, amplifier circuit, the signal processing circuits, and all that. And another thing is that we can have a P-type and N-type material in a single sensor package, in a Hall sensor package. The typical dimensions or geometries, of Hall sensors, that means what of the size, length, and dimensions, are from 100 micron to 10 micron. That means 10 micrometer, 100 micrometer, or even smaller than this. That means we can design the Hall sensors which have a dimensions of this much, 100 micron square or rectangle, or 10 micron rectangle or square. Okay, and the circuit density, that means the components of the circuit onto a single chip, that circuit density is extremely high, allowing complex circuits. That means we can design many components. If we have a very large complex circuit which does not actually include single Hall sensor, it is a circuit which is used for some other purpose. For example, there's a transmitter, or there is some another machine which is using this their Hall effect in your lab, or there are other which are based on this sensing of the magnetic fields, and then we can use this Hall sensor in that complex circuit inside it without taking too much of space because of its low dimensions. There are different characteristics what we should keep in mind while we are working with a Hall sensor. There are various factors. The important one is that that is called sensitivity. So the characteristics of a Hall sensor or a Hall, these can be all, these are also transducers because they convert one energy into another, one form of energy into another, or one type of signal into another. So characteristics of these Hall sensors, like we have sensitivity or gain. So see that, you know that Hall sensor actually determines the Hall voltage, which we have seen. It is this. Since Q is constant, number density is the already determiner of a particular doping concentration. What is the charge density of that material? Thickness is also known. What is varied? I and B. So we are varying actually I and B. So sensitivity can be varied by varying either I or B. So at that time we have sensitivity. It is called current sensitivity. It can be a current sensitivity, or we can have voltage sensitivity. Voltage sensitivity. That means how its output is, how much sensitive this Hall voltage, that's the output, is to current or to magnetic field, or sorry, yes, to voltage. Because what we are changing actually, this current or the voltage will change any of these two, I and B. That means, so what we are measuring? We are measuring voltage, volts per Tesla, because magnetic field we are keeping actually constant. Because whatever you apply magnetic field during a particular, you can keep it constant, or you can vary by varying the current in the output and the voltage to change this current. So two factors can vary it, either current or a voltage. So voltage per Tesla per ampere, that means how much with respect to this current voltage is changing here. And we can have voltage per Tesla per volt. So these we can determine the sensitivity into these two different ways. The voltage sensitivity of a particular this Hall sensor has been seen that it is equal to, it has been observed up to 0.035 volt per Tesla per volt. So that means this small much, it is it is sensitive, and it can have a very small change by changing the voltage or either current. So this is the order of change, or how much change is there by changing the voltage. It is per unit volt actually. When we mention the units, these are per unit measurements. And another thing is there which we should take care of, that is noise. So we should know actually sensitivity before working with a Hall sensor. The reason is that errors may come while you are measuring a quantity. You should know that how much change is there by changing a unit voltage or unit current, 1 ampere, 1 microampere, 1 milliampere. So that should be known, because during measurement, if there is a change which is less than this, you cannot be able to measure that. Or if it is a change of this order, you are not sure what this change is or how much change is coming out. You should be aware that what is the change because of fluctuating the voltage or changing the voltage, and what is the change which is actually coming in because of the sample, because of our measurement, because we are measuring Hall sensor for some particular measurement. So what is the change which is because of that measurement, and what is the change because of changing the input parameters by Hall sensor itself? So noise. Generally, these noises are called as electrical noises, and they appear at output. They appear at output. Noises are mainly the main noise which is here. There are actually two are discussed. Two noises are discussed. One is Johnson noise. This is also called as thermal noise, because this can, whenever there is a noise, what is thermal noise, we will tell. This is dependent on frequency. It is also called as 1/f noise. That means your signal is coming, and what is the change in the frequency of that signal? That frequency will induce a signal noise, and this will also, this thermal noise will be also induced there. So what is Johnson noise? Actually, is a thermal. That means this Johnson noise, I will write it JN, thermal noise. Thermal noise. Yes. So this thermal noise, actually, it appears due to random and thermally induced motion of electrons through the conductor or a material through sample. Sample means it's a semiconductor or a metal sample. So that's why it's called thermal noise, because whenever there is a current moving through the sample, that there may be the scattering of electrons, charge carriers with ions, with sample boundaries, or so that may create some heat loss in the form of energy loss in the form of heat, which will be finally actually a thermal noise, which is generally called as a thermal noise. One. There may be also a frequency dependent noise. There also exists sometimes a frequency dependent noise. At low frequency signals, when you have a low frequency signals, and this is also called as 1/f noise, or it is called as flicker noise. Flicker noise. So this Johnson noise or the thermal noise, it limits how small signal can be recovered from its output. That means if there is noise, the output signal may be distorted. The output signal may be disturbed, and the small signals are difficult to measure at that noise. We can use then what we use actually, we use those sensors which have very low impedance. Okay, that means which have very low resistance, which have very low scattering actually, so that there is not much of the scattering in the of the charge carriers, and not random motion of the charge carriers, which can create a large resistance or large impedance in the circuit. So low impedance circuits are actually used so that we can have we can measure the small signals by avoiding that thermal noise. Now, its applications. What are the applications of Hall sensors? It is used almost different category, for different applications. For example, one is used in automobile as well. It is used in for measuring the sensitivity of this different instruments. It can be used in, you already know how we measure those magnetic fields in the lab. It can be also used to measure different electrical quantities like current or voltage, and it can be used for different instrumentations actually, and some of them we will discuss one or two. Let us discuss first one. Hall position sensor. So that means because we have time, okay. So it may change, it measures it senses a change in the position of some object. That means whenever there's a change of an object, a Hall sensor senses that. That is how it can be used. That means it senses that position. That is why it's called position sensor. And how it is measured, how it is done actually, I have, so can you see this? Sorry. There are different designs actually, vertical configurations. These are the different configurations. You can go through it. This is Hall position sensor. See here, I will show this. For example, see this. Can you see the figure? Yes. So this is a one of the Hall position sensor. I'm sorry. Yeah, now it is okay. This is a Hall position sensor, one of the Hall. This is another one. These are two different this configurations, and they have been made by two different companies. Now see, there's a magnet here. This is the magnet, and this is the Hall sensor. So what it does actually, whenever there's a moving this van or a blade, simply a blade, whenever it is moved in and out, what happens? It actually changes this. There's a magnetic field, and this magnetic flux actually changes to this sensor. The magnetic field will change with respect to this sensor because you are moving in and out some position. There's a magnet, so its magnetic field effect to this sensor will change because when you are giving the relative motion to this object, this blade, moving van, and in that sense, that change in this position is directly proportional to change in the magnetic field which is sensed by this Hall sensor, and then this change is taken in the output. This is the simplest procedure how it works actually, and it alters actually the magnetic flux which is coming from this magnet. So this is how it works. It's the simplest one. This is circular one. This is a rotating van. There's a north-south magnet. There's a Hall sensor here. There's a magnet. There's a rotating van. Whenever this position changes, the magnetic flux, which is feel by this sensor, it changes actually. So when it changes, that change is detected in the output of this circuit. Now the another one is we have the one which is Hall current sensor actually. For Hall current sensor, this is a Hall current sensor. Now what is actually here done? There is a current carrying conductor. This current has to be detected actually. This current has to be detected by the Hall sensor. This is a Hall sensor here. This is Hall sensor, and here it is shown. So Hall sensor is shown. So the current carrying conductor has, because this is current, it is varied. It moves in this, and this is a soft iron core which detects any change in the current, and it's a magnet actually, magnetic core, soft magnet core, and any change in the current will change the magnetic flux in this coil. Okay, and that magnetic flux is detected here by the Hall sensor, because whenever you change that B, that VH changes, which is BI divided by, what was that? That was Q, NC, and TH. So whenever this B changes, because of this I, that VH will change, and that will Hall voltage output is taken here. Okay, and so there's a current carrying conductor. This current, if it changes, this current, there is a change in the magnetic flux, because according to Faraday's law and Lenz's law, that change will be picked up by this soft coil, soft magnetic core, and that will change the magnetic field actually, which will change this VH here. So this VH is when it is changed, we get the output. What is the change in the current? So that is how the current carrying Hall current sensor works. There is another application, and I will show you door security system. I will give it to you. Check it at home and do it here. Okay, see how it works. Now, this is what this Hall effect we have discussed. It is working principle, its applications, characteristics, and how it can be used. And there is one more example of that door lock system. Please do it and see it how it is working actually. No. Then there is a one important actually. It is important in the sense that the physics is very interesting, but it is a bit, you need a very long, you need a very good knowledge of the superconductors actually. So that is SCID. This is another Hall, this sensor. Sorry, not Hall sensor. It is a sensor. It is a magnetic sensor actually. It employs, it detects magnetic fields, and it senses magnetic field. So that means we can apply magnetic field and sense its change. I already told you that we can measure the magnetic field by taking some quantity, which is then converted into the magnetic field in the output. We can have a magnetic field input, and we can measure this magnetic field via a sensor in the output as well. So that sensor does not give us directly the magnetic, but it converts that magnetic field in another quantity, which is then again converted to an output, the magnetic field. So SCID is actually this super conducting quantum interference device. This S is not needed. It is simply SCID. SCID is plural. So device. So that means it is a superconductor. The quantum mechanical effects are there, and there's an interference, and these all phenomena are involved in a single device that is called, which is we refer as SCID. It is a SCID, or sometimes it may be a SCID magnetometer. So SCID magnetometer means that it measures magnetic field, or the magnetic moment actually, not the magnetic field exactly, magnetic moment. The sensitivity of SCID is very important for detecting very small magnetic moments, magnetic fields or magnetic fluxes. Because when you have a magnetic moment, you have a magnetic flux or magnetic field, and that is a magnetic flux. And it can measure up to the field 10 to the power minus 14 Tesla. This is its strength, that it can measure up to this much of small values, 10 to the power minus 14 or 10 to the power even minus 10 to the power minus 15. This much. So this is a threshold, its threshold, the minimum value it can measure, 10 to the power minus 15. And so we need a superconductor actually for this. I will give you an idea that, the idea is that, let me see, this one, yes. The magnetic field, magnetic field of heart, human heart, it is of the order of 10 to the power minus 10 Tesla. And the magnetic field of brain of a human, it is 10 to the power minus 13 Tesla. So that means the SCID can be used for measuring the magnetism in living organisms as well. That is, one is called as biomagnetism. Log in again for 5 to 10 minutes, not more than that. I will leave you early. So please log in again, because time is up for this session. It will be less than 1 minute. So please log in if we need. Now, what actually is SCID, how it is, what it consists of. SCID is not a complicated that much of structure, but it has a simple ring. It is a ring structure like this. And this ring is not a single ring. It is not made up of a single component, single material. It is actually a ring which is made up of two junctions, two here, one junction, here is one junction. So you can think of it like this.